In this video, we discuss isolated singularities. So here is a quick definition. Z equal to A is an isolated singularity of F if there exists R greater than 0 such that F is analytic in the ball with center A and radius R less A itself, but not in the ball with center A and radius R. Okay. So what are we saying? Here is a ball with center A and radius R. All right. So this particular point A will be called an isolated singularity. If for some R, that means if there exists a ball such that the function is analytic at all points in the ball except the center, that's it. So let us look at some examples. Fz equal to 1 over z. So in this case, z equal to 0 is an isolated singularity. Okay. Now the isolated singularity could be of several types. A, removable, B, pole, and C is the essential singularities. We will discuss only B. That is poles. Okay. So when is a singularity a pole? Definition. Let z equal to A be an isolated singularity of F such that limit z tending to A mod F of z is infinite. So if this happens, then A is called a pole. Okay. Example. So fz equal to 1 over z this itself is an example. It is an isolated singularity and also a pole. So if you look at the modulus of this and let z tend to 0, okay, the value that you get is infinity. Okay. Another example could be if you take f of z equal to 1 upon z minus 1, okay, then z equal to 1 is a pole. Fine. Now these are some very simple examples. Now I give you a classification of poles through the Laurent series. Okay, so what do we want to do? So let us first understand what a Laurent series is. Let f be analytic in a ball with radius r and center a less a itself. Then, this is a theorem, then f of z can be written as sigma n equal to minus infinity to infinity a n z minus a raised to n. Alright, that's a theorem. This is true for, suitable constants for giving this vague for suitable constants an and going from minus infinity to infinity. Okay. So if z equal to a is a pole, then what happens is the terms which are corresponding to the negative powers of z minus a get restricted. So if you are looking at a minus 1, a minus 2, a minus 3 and so on, it doesn't go on and on. It stops somewhere. That is how the poles get classified. If z equal to a is a pole, there is an m greater than 0 such that a minus m is not 0 but a n is 0 for all n less than minus m. And in such a case, you say that z equal to a is a pole of order m. Okay. In this case, then A is called a pole of order m. Example. So if you look at f of z equal to 1 over z, then 0 is a pole of order 1. Let's look at f of z equal to 1 over z minus 1. Then 1 is a pole of order 1, also called as simple poles. Let's look at f of z equal to z plus 3 upon z minus 2 plus 1 upon z minus 2 cube. Then in this case 2 is a pole of order 3, and so on. Okay. Now we discuss residues, and after that we discuss the residue theorem. Okay, so we just looked at the Laurent series, and in the Laurent series, if f is analytic in the ball with center A and radius r less a, then you have the Laurent series, and I will write this in a slightly different way now. F of z is equal to sigma n equal to 1 to infinity a n z minus a raised to n, and then there are terms in the negative coefficients, negative powers of okay, so I have a minus 1 upon z minus 1 plus so on. Okay, a minus 1, which is the coefficient of okay, this is a, z minus a raised to minus 1 is called the residue of f at a, and the notation that we will use will be residue of the function f at the pole a. So this is the notation that we will use. Okay. Example. So if I look at f of z equal to 1 over z, okay, so obviously a is 0 over here, so you can think of this as an expansion like this, where a0, a1, a2, etc. are all zeros, a minus 2, a minus 3, etc. are all 0, and a sub minus 1 is equal to 1. So what is the residue of f? The residue of f is the residue of 1 over z at 0 is equal to 1. Okay. If I look at f of z equal to z plus 3 upon z minus 1 plus 2 upon z minus 1 cube, then what is the residue of this function at z equal to 1? So the residue of f at 1 is equal to the coefficient of 1 upon z minus 1, which is 3. So that's how we work with residues. Okay. Now I will state the residue theorem, and before I state the residue theorem, I'll give a formula for working out the residue of something which is not as easy to see. Okay. So there is a theorem, and the theorem is the following. Let F be a pole of order m. Okay, then what happens is g of z can be written, so you can write down a g of z in this particular fashion, f of z into z minus a raised to m. And if you do that, let me call this as let. So this is a let g of z be this. Then the residue of f at a is 1 upon m minus 1 factorial, that's the m. The m minus 1th derivative of g evaluated at a. This is a nice convenient formula. So if m is equal to 1, for example, then the residue of f at a is 1 upon 0 factorial, which is 1, and g of 0 is just the value of the function at the function g at a. Okay, so no differentiation, this is no differentiation, and which is same as this, etc. All right. So let's look at an example or some examples. So if I take f of z equal to 1 over z, then what should be my g of z? Let g of z be equal to the function multiplied by the factor. So f of z into z, which is equal to 1. F of z is this, which is equal to 1. So what is the residue of 1 over z at 0? It is just the value of g at 0. So it is just the value of g at 0, but then g is a constant function, so this is equal to 1. Okay. Let's look at another example. F of z equal to z plus 3 upon z minus 1 plus 2 upon z minus 1 cube. Okay. Let g of z be equal to, so z equal to 1 is a pole of order 3, z minus 1 cube as a factor multiplied to f of z. So what we have is z minus 1 cube into f of z, that means z plus 3 upon z minus 1 plus 2 upon z minus 1 cube. This becomes z into z minus 1 cube, and then one of the factors gets cancelled, so 3z minus 1 square and a 2 over here. So what is g dash z? G dash of z will be this into the derivative of this, which is 3 times z minus 1 square plus this into the derivative of this plus this into the derivative of this, that means 6 times z minus 1 plus a 0. Okay. So 2 terms from here, 1 term from here, and 0. Okay. And what about the second derivative? Okay. So this is 3 times of z into the derivative of this, which is z minus 1, and then this into the derivative of this, plus 3 times z minus 1 square plus 3 times z minus 1 square plus 6. Okay, I want to calculate the residue, so I have to calculate this at z equal to 1. Therefore, g dash dash of 1 is, so I get a 0 from here, a 0 from here, a 0 from here. So what I get is just 6. So what is the residue of f at 1? It is 1 upon 1 factorial g, that's a pole of order 3, so 2 factorial, the derivative of the second derivative of g at 1. This is equal to 1 upon 2, g dash dash of 1 is 6, and therefore the answer is 3, and that is what you expected. The coefficient of z minus 1 raised to minus 1 is the residue, and it comes out to be the same. Okay, now coming to the residue theorem. What does this theorem say? So let there be a closed curve gamma, and let us have a1, a2, a3. These are the poles, isolated poles. Okay. Then in short, the residue theorem says is that integral of f of z dz over gamma is 2 pi I times the sum of residues. Sum of residues. Okay. So if so for this particular example, it will be the residue at a1 plus the residue at a2 plus the residue at a3. Okay. Now this curve should not be passing through a1, a2, a3. It should enclose. It should properly enclose the poles. Okay. So if there are k poles, a1, a2, a3 up to ak, then you have the sum of all the k residues over here. Let us look at an example. Okay. So I will take f of z to be equal to e raised to z plus 2 divided by z minus 1 and z minus 2 square, let us say. And the question is to evaluate the integral over mod z equal to 3 of f of z dz. Okay, so let me draw the diagram. With radius 3, I draw a circle. I have the point z equal to 1, z equal to 2, and here let's say z equal to 3. Z equal to 1 is a pole of order 1, z equal to 2 is a pole of order 2. As per this theorem, I should find the residues at 1 and 2 and then apply this formula to work out the integral. Okay. Now, what will be the residue? What will be the residue of f at 1? Okay. So this is going to be the value of g. Okay. So let me divide this into two parts. Z equal to 1 is a pole of order 1, right? So z equal to 0 is a pole of order 1. Let me write down this function g1 of z. Let g1 of z be equal to z minus 1, order 1, so the power is 1 into f of z. Okay. So this is e raised to z plus 2 divided by z minus 2 square. Okay. And this implies that g1 at 1 is equal to, put z equal to 1 here, so what you get is e plus 2 divided by, so 1 minus 2 is minus 1 square, which is 1. Okay. So what is the residue of f at 1? The residue of f at 1 is 1 upon 0 factorial g, no differentiation, the value of g as it is at 1. Okay, and this is e plus 2, so that is the residue of the function at 1. I have to now calculate the residue of this at z equal to 2. Okay, so let me take put the calculation as part B. Z equal to 2 is a pole of order 2, right? Let G2 of Z be Z minus 2 square. This is a pole of order 2. Okay, f of Z, which is Z minus 2 square, and the function f of Z is this. Okay, this cancels with this, and what I have is this. Okay, this means I have to calculate G2 dash of Z. This is equal to Z minus 1 into the derivative of this minus e raised to Z plus 2 into the derivative of this divided by Z minus 1 square. That's the usual quotient rule. And this means that G2 dash at 2 is equal to 2 minus 1 e raised to 2 minus e raised to 2 plus 2 divided by 2 minus 1 square. And how much is this? E raised to 2 minus e raised to 2 minus 2 divided by 1 square. So I'm left with just this. What does okay, so the residue of f at 2 is let me write the formula: 1 upon m minus 1 factorial m minus 1th derivative of g evaluated at the residue 2. Okay, m is 2, so I have 1 upon 1 factorial g dash differentiated once, g differentiated once. This has been calculated here. Okay, there's something missing. No, it's okay. Minus 2. So what does the residue theorem say? So by the residue theorem, the integral of this function over this is the sum of the residues. It is 2 pi I times the residue of f at 1 and the residue of f at 2. This is 2 pi I. The residue of f at 1, we had calculated it earlier, it is e plus 2, and the residue of f at 2 turns out to be minus 2. So the answer is, this is 2 pi e times I. That's all in this video.